Okay, let's start. This is day 1, 1600 hours, and with me is Arjen Fijn from the Netherlands, presenting 10 gigabit Ethernet monitoring live. Please welcome him.
Okay, thank you. I hope I can all entertain you. So many people here. So I'm daring to do a live demo of 10 gigabit monitoring, and let me first introduce you to the demo setup. On the top we have a traffic generator that generates 10 gigabit Ethernet traffic, and I'll send that to a switch below. And between this switch there are 2 wires, traffic generator and switch are 2 wires to send the traffic over it. And we're going to monitor the traffic that is on, let me see if I can point you to that, on here. For that, and now I have to do another trick. For that we have to go to the screens. Yeah. The screens that we have. What you see here is the output of the traffic generator, sending right now about 1,000 frames a second, and receiving a little less. Here we have Hysterics is one of the screens of the monitor box. Lazarix is the switch I was talking about, and that's what we're going to use for the demo. So, and I forgot to say first, please ask questions in between. This is a live demonstration with lots of numbers on text screens, a window screen you might not be familiar with. So if you think, hey, I don't understand it, please raise your hand and you will get a microphone, and we'll try to get it, to get it more live and understandable demo. So, first, we'll send traffic about 1,000 frames a second to this switch. And here, on the other port, we send also about 1,000 frames a second, but hey, we don't receive anything. So, this switch between this traffic generator, that might be broken. Who thinks it's broken, actually? Because I think it's broken. Because I would expect that the traffic that I sent in would come out, would go through the switch and come out through the other port. And apparently it doesn't. So let's have a look at this Ethernet switch, which is here. And the first thing people on layer 2 switches do is look at, hey, do I learn MAC addresses behind the ports? And we do that with the command show MAC address. And we see that the switch learned 2 MAC addresses, and that are actually the MAC addresses I expect. So here's something really, really wrong, because I see here MAC address 1, 2, 3, 4, 5 behind port 2.1, and MAC address A, B, C, D, E behind port 2.4. So, and there is, the H is 0, so that means that the switch actually learned these MAC addresses on the port. And still there is no traffic going through the ports. If you look at show interfaces, interface says 2.1. We see that we receive input rate, we receive about 500 packets a second. Well, the traffic generator says it's at 1,000 frames a second. And on the other port we receive about 1,000 frames a second. And hey, it says it transmits about 500 frames a second. So let's go back to this traffic generator, and that's exactly what we see. We send, and I hope you can see that. Is this too small? And, we'll receive about 0 frames here, so nothing is coming from this port to this port, and 1,000 frames here, and about 500 frames are coming out of this switch. So the switch seems really, really broken. Is it really broken, is the question, of course. And as you might guess, looking around on the switch, let me switch it on. We cannot really see. Live demos are difficult. Looking at the switch, we see these frames coming in. We see about 500 frames coming in. Well, the traffic generator says 1,000 frames, so let's look at what is coming in. Let's look what is coming into the input. So for that, we are going to look at 10 gigabits. And we're going to switch to this window. It's working, yeah. And this is the monitor box I want to demonstrate. And I'll set a filter to look at the traffic, and I'm going to look at the traffic. And oh man, there's a lot of traffic coming into this switch. So, wait a minute. So let's see if we can do not the traffic distance. I have this in my distance for A, B, C, D, E, which is the traffic I'm sending over this link. I'm sending traffic towards A, B, C, D, and let's see if there's other traffic. So I'll set this filter, and I'll look at TCP dump again, and hey, I see traffic from a really, really unknown source. Anybody an idea what kind of traffic this is? Nobody? Okay. Let's ask a more smart program, T-Shark, which has the sectors for lots of different Ethernet frames. And we see that this is actually a pause frame. So our coming pause frames are coming in to the switch, making the switch block the traffic that it's sending out on that port. Pause frames say, if the switch receives a pause frame on its port, the pause frame actually says, please stop transmitting traffic for a while. So actually only by looking at the traffic, we could see that this was happening. And I'll explain later on in slides what was actually happening. But only looking at the traffic that was going over the wire, we could see this. The switch doesn't have any counter of saying, I have so many pause frames coming in. Because pause frames are really processed early in the ingress path of the switch. And I'll try to explain that right now. So, this was a bit of live work.
Oh, I think it works. What's up with those pause frames? I don't remember seeing them in like a normal 100 megabit Ethernet on my switches. So
yeah.
Is it possible to like generate them and like make the switch pause on every port, or is it just the port that
it's the port that receives the traffic on. There it's
so I can just block myself.
You can block yourself.
Okay.
Yeah. You might be able to. No, the switch will receive it. So when you look at this traffic generator was sending these pause frames over this link to this Ethernet switch here, and it will make that the traffic from here to this port is being dropped, basically. And on the switch, we do show MAC. We just learn the MAC addresses from the traffic that is coming in here. But the traffic is really, the pass frames are really dropped early in the ingress path of the switch. So if you send it, a good switch will drop it right away, or process it and drop it right away. It will not switch it to another port, so you cannot block anybody else with it. So let's have a look. So I'm now going to do the real slides and not clumsy with screens. I'll go back to another demo later on. So what's the agenda? I first start with an example on slides, which is basically the same thing as I just showed you. Then I will try to tell you what are actually the problems with monitoring on 10 gigabit Ethernet on these fast links. Why a general purpose computer, and also a really fast general purpose computer, is not fast enough to do this. I'm going to tell you a bit on monitoring with switches and using the mirror port feature on these high links. Then I'm going to tell you the solution we made for that, and how the hardware is built up, the firmware in that hardware, the software around it. That's all in a general overview. Then I'm going to in a bit more detail, and later on you may see some more confusing screens going over the beamer. So let's start with the example. I work for a network that normally connects BGP routers, and I symbol that with this circle on the left, and it's now represents a 10 gigabit router. That is connected to all photonic switch. That is a fiber switch that sends the light that is coming in is switched to another port, to a redundant switch fabric, a switch part. Actually, for every port, for every BGP router, there are 2 separate switches, and this device in between connects this router to one or the other Ethernet switch. And that's also very handy if you have a new switch, and we grow with traffic all the time, to put this new switch into production and really quickly get it out again. So we had this new switch, and we connected it to our switch park. Everything looked fine. And we used this device to move this BGP router on the left into production, and immediately that router wasn't very happy. So we switched back, and logically you think that this new switch, that new element you introduce into your network, is really the fault. Would make sense, I think, because that's a new element in your network. So let's start debugging this thing. I'll tell you how the vendor of this switch did that. They were actually very smart. They said, let's put an access list on this switch, and then look at the counters of this access list. It counts on ingress the frames, and on egress the frames it should go out, right? And if these numbers are the same, then the switch is switching. So to tell you that, traffic is coming in here and it goes to all kinds of blocks in the switch. The phi is the optic, where light is being converted to electrical signals, goes into the MAC chip, that's actually that thing that does pulse frames, and goes to a packet processor. And the packet processor processes the access list. So the access list counts on ingress, the number of frames, goes to traffic manager, switch fabric, comes to another traffic manager, comes to another packet processor, and is counted again. And if these numbers are the same, then we know that this whole path works. We don't know if the egress path works. But the vendor says that cannot really be a problem, because this here, this MAC chip, that's the same chip, ingress and egress. It's the same silicon, and if there is a problem in that chip, we will see it on both. We would see it on the ingress as well. That was their defense. And, well, as you can guess, the access list counters were exactly equal. Number of frames coming in, number of frames coming out were exactly equal. So we were really, really puzzled, and also the maker of the switch was really, really puzzled. And it went on for weeks. I had this 10 key monitoring project, and I said, okay, I'm going to put this monitor project in, and I'm going to watch what's here on the link. And guess what? We saw these pulse frames coming in. These pulse frames were coming in from the switch fabric, from the switch park that was live, that was carrying traffic, which we thought was fine. But it wasn't really fine. It was broken. And actually, it took about 2 minutes to figure out that these pulse frames were the problem. Another group in the switch vendor fabric, switch fabric factory, said, "Oh, hey, we know this problem. We have already a software fix for it." And yeah, in literally minutes, we know what the problem was, and the problem was solved. So yeah, this was really, really good example of how useful this 10 gigabit monitoring is. And yeah, that was a good thing to do. So what about 10 gigabit monitoring? How do we do that? Well, let's first address what the issues are. Normally, passive monitoring you do by using a mirror port feature, or other vendors call it a span port feature, on the switch. And what it does is it copies the traffic that is coming in, it copies that to another port. And on that mirror port, you connect normally, or we do that, we connect a general purpose PC with a normal NIC, and we use all kinds of tools based on libpcap, like TCP dump and T-Shark and that kind of tools, to see what kind of traffic is coming out of the mirror port. So let's first look at the problems with this general purpose PC. Well, 10 gigabit Ethernet is fast. Is a lot of frames per second you can send. On 10 gigabit Ethernet, the maximum frame rate is 14.8 million frames a second. That is only with very, very small frames, because you have a small frame, takes the smallest size frame, 64 byte, takes about 50 nanoseconds to be transferred over the line. Then there must be a gap, an interframe gap, and that is on 10 gigabit. That's actually on all Ethernet standards. It's 12 bytes pause, and that takes on 10 gigabit 9.6 nanoseconds. And then there's the next frame. And with all small frames, you get 14.8 million frames a second. With larger frames, the frame rate is getting less and less and less. And the frame size is getting bigger and bigger and bigger, so with larger frames you get more data throughput with less frames per second. And so I was wondering, okay, what can we do with a normal PC with a normal Intel 10 gigabit Ethernet NIC, network interface card? And so I set up some tests. And the test was like this. I'll try to send traffic. And then I know how much traffic I sent with this traffic generator, and then I'll reduce or enlarge the interframe gap, reduce the frame rate or the data rate to a level that I see that I capture all frames. So at what level do you see everything? Well, it surprised me. It was not that bad as I thought it was with this. Well, it was quite a high-end Woodcrest Intel CPU machine. On the largest frame rate, it was about 10% of the traffic. That's here. And as you can guess, the lower the frame rate went, the higher up I could turn on the traffic to see everything. And at a certain point, it became a constant. And this was done by a test with, go back to one slide, where I sent 1 million frames of something I don't want to see, and then 1 frame I want to see. So it reduced the frame rate until I saw this 1 frame, all the 1 frames that I was sending. If it doesn't make sense, please raise your hand. So, yeah, with a normal PC, you can go up, depending on the frame size, between about 10 and 80% of the traffic, but not 100%. And if you do troubleshooting, you want to be able to see everything. So I did some more tests, like 1 out of 16 frames, and then I could only see 2 if the bandwidth usage was about 2% to 37% of the traffic. So that was a graph like this. Well, you see, a normal general purpose PC cannot reach, yeah, that's basically the conclusion. A general purpose PC is not fast enough to capture everything. But there's another problem with this setup, with this mirror port. So I wanted to test that mirror port as well. So the device on the test was a Foundry RX series switch. And this was the test setup, 2 testers going to the switch, and one of the testers was just sending traffic between the ports. Basically, what we started with. And without any mirroring, on all frame sizes, the throughput was 100%. So basically, this switch works. It can work line rate on 10 gigabit Ethernet. But as soon as we switched on mirroring, we could see that the traffic here was dropping if you do that full line rate. So it was reducing the line rate again until all frames sent through were received. And what do you get when you only look at ingress traffic? Well, then you can go up to about 56% of the traffic, depending on the frame size, up to 70%. So it's between 56 and 70%. Above that, you have frame loss on your traffic that is live, not the traffic that you are monitoring, the traffic that you are switching. So this is a quite interesting thing. Turning on this feature might harm your traffic. So we did a series of tests. This is on egress. It's about the same result. When you do copy traffic from both ingress and egress, so input traffic and output traffic, to the same port, you go between about 45 and 50% of the traffic you really can send. And the worst case is if you send things to 2 ports, then the worst case is that you can only have throughput until about 37% of the maximum. So the conclusion is that the mirror port feature may be harmful. In the best case, you can use about 70% of your bandwidth, and in the worst case, you can only use 36% of your bandwidth. So, yeah, this mirror port feature seems to be, well, it's at least dangerous, and it might be wrongly designed. Well, actually, it's a result of the design decisions. A mirror port feature means that you have to copy the traffic somewhere. You have to get the frames that are coming in and copy that to another port. That means that you have to have more bandwidth into your switch than you normally use. And more bandwidth into your switch that you normally use will mean that you also have to pay for that. And we, buyers of switches, we want to have a cheap switch. And we go for the cheapest switch with the most ports. So vendors say, okay, this is a special feature, not everybody has to use this. So we're going to use bandwidth in our switch that we normally use also for other things. Basically, if you want an error-free mirror port feature, you have to build a switch that is twice as fast as you will use. There's another issue with that is, yeah, where do you copy that traffic? And the decision was made by the maker of the switch to copy the traffic in the ingress path. Here, in this packet processor. This traffic is coming in and there's a copy being made of the traffic. So the bandwidth here, between the packet processor and the traffic manager, is about 12 gigabits a second internal in the switch. And you can only use 12 gigabits per second. So if you have 10 gigabits and you make it 20 gigabit, you will have frame loss. That's the idea. And why do they do that there? That's because traffic is being divided over different switch fabric modules. And that gives redundancy, that gives lots of ports, it has lots of benefits, but it has the disadvantage in this sense that you have to copy your traffic quite early in your path, where you don't have that much bandwidth. So it's all the results of a design decision. And it's not only the maker of this switch foundry that has this problem. Every switch maker vendor of this high-end switches has this problem. So we had a problem with monitoring 10 gigabit Ethernet. We could not use a normal purpose PC, and we could not use this mirror port feature. So we had to have some solution for it. And that solution that you quickly figure out, okay, you should not do anything on this Ethernet switch because that will give packet loss, that will give frame loss. We should monitor before it. We should monitor on the wire. And luckily, as you already saw in one of the first slides, we have this fiber switches in between. And well, what we can do is we can use this switch to put the traffic onto some kind of device where the traffic is just repeated between two transceivers. So traffic that's coming in is going to this device, coming out again, and vice versa. And in this device, we copy that to the PC. But the PC is still not fast enough. So what we have to do is actually reduce the data rate to a level where the PC can handle it. So you have to have a device like that has a block, a logical build-up like this. Two transceivers on the top, a repeater, a layer 1 repeater, that repeats just the traffic between these interfaces and then copies it to some kind of programmable filter that can filter that at line rate. And then the traffic is being really, really reduced until a level that the PC can handle. And then we have some kind of driver that makes it look like a normal Ethernet interface, so we can use the software we all know. This is the concept of the device I am demonstrating here. On the top, everything is done in hardware. Everything is done line rate. And on the bottom, things are getting slower. This is the whole idea of this device. So we looked at devices that are being made, and we came out to what is now made by Force 10 Networks, the NTP-10G card. That's a network interface card which is actually part of a security system, and that security system is to do intrusion detection on 10 gigabit internet, also do prevention, so block traffic that you don't want on 10 gigabit internet. And this card is all built around programmable hardware. And this programmable hardware that has a nice feature that you can make your own software for it. And that's what we did. So let's just have a look at how this card is being built. It's actually built around 3 main programmable devices. And on the top we have what we call the front-end FPGA. And in the front-end FPGA there is this repeater where we repeat the traffic between the 2 interfaces. The card has so-called XPEC interfaces. This is here are the interfaces, and this is the front-end FPGA. XPEC is one of the form factors, transceiver form factors of 10 gigabit Ethernet. So traffic is being copied between these 2 transceivers and being copied down over this bus towards the block below. And what is going over that link, over these arrows, that are 128-bit wide blocks of data. And the first block contains the whole Ethernet frame, including its preamble. A preamble is something that was used in 10 megabit Ethernet to clock the frames. 10 gigabit doesn't do that anymore, but the makers of IEEE decided to make it completely the same as the old 10 gigabit, the old 10 megabit Ethernet and 100 megabit and gigabit Ethernet. So it has this preamble. Then it is followed by the destination MAC, and then you have a little bit room left, 16 bits, and that's where the source frame starts. And then once this is on the bus, there is a second word which contains the rest of your data, or the rest of the 128 bit of your data, and a third word, and it goes on, and goes on until you reach the end of the frame. And then you get the next frame. And that's ending up at the backend FPGA. And the backend FPGA is really the heart of this whole system, because that is where we filter the traffic, where we reduce the data rate. So how do we do that? Traffic is this 128-bit is being received in a frame data register, 128 bits. And then we really have to process it. And that processing, that is something that you have to do fast. And actually there is a trick for that. Is to process this whole 128 bits all at once with different processors. So we have an array of processors that can be applied on this 128 bits all at once. They have a register, instructions to get the instructions. The data is being processed and then being reduced into what I call reduction network, and that results in 1 or a 0. Should this data be copied to the PC or should it not be copied to the PC? If it should be copied, then the match memory, where all the 128-bit words altogether are being stored, if that matches, then it goes to the PCI Express and to the PC. So this is a pretty straightforward concept. The really tricky here is that you have one single register of data and lots of processors that process it all at once. Because you have not too much time to process it. You cannot make a whole decision tree to decide what you want, which is basically what you do with a normal processor if you program in a sequential language. So that was, in a real overview, the hardware. Which is in a different drawing. That's here below. That was the hardware. And we need to make some software on top of it. So the software consists of two kernel modules. The software is made for Linux. On the right side, a kernel module that is basically the Ethernet driver. It acts like a normal Ethernet driver and presents the card as a normal Ethernet interface to the user. And that normal interface, you can just use your normal hardware, your normal software on it. And there's another kernel module that takes a piece of memory, and from that you can control the card. And that's the input and output. For the output, there's just a polar reading out counter values, and give that to some output. And on the input, that's a bit more difficult. So let's have a look at the input. On the input, it takes, and you might have seen that already in the demo, it just takes from standard in the filter expression that are used by libpcap, like not ether source and then MAC address. This being processed by Alexa in a parser, very, very straightforward. Many programs work like that. And that actually recognizes the addresses and recognize the operators and transfers that into some kind of internal expression. What is being done is the data is being taken. So you have a pattern of data, you have an offset in your frame you want to match, and those are being matched together and being treated as one variable. And this is being stored internally and then processed by the Quinn-McCluskey algorithm, or QM algorithm, which is a fairly well known, if you are into this algorithm, that changes this expression to what is called its disjunctive normal form. It's sum of products. And this is really important because remember we had all these little processors all working together. That means that, and all working all together, all at once. That means that you have to cut your expression into different pieces. And this is really key in this whole system. Once you have it in this disjunctive normal form, or this sum of products, then it's really easy. Then it's just a matter of getting it into the registers. Well, that's being done by a module called the register mapper, and that just takes this disjunctive normal form and puts it into the instructions that are being that are recognizable for the FPGA. So this is an overview of the system. Any questions about that? There is a hand, I think. Yeah.
How do you cope with VLAN tags and IP options changing the header length?
Yeah, that's a very good question. Not yet. I have an idea on how to do that. Is that you use some of these internal processors to recognize, let's say, a VLAN tag, and say, okay, I have to shift everything I got. I have to add a certain number of bits to it. That's how you can work with shifts in the data that are really fixed. For options, especially IPv6 options, I have to do the same, I guess, to do that. IPv6 is actually easier because you see the, you know, with every frame you get where you have the, with every option you get where you have to add the offset. IPv4 options, yeah, I guess I have to hard code those into different, use a number of processors to do that. But yeah, we are a layer 2 network, and it's really, really rare that I have to go that deep in the traffic. That's, I guess, when I need it, we'll program it. That's the idea. So, okay. Any other question? Excellent question, by the way. Okay. I'll go into a little bit more detail on how things are being processed. Let's have this not eater source thing here. Expression, and it's getting its first data word in, and in that first data word there is a little bit of piece of data we want to process, the first 16 bits of this source address. The processors can process per 16 bits, so we need one processor for that. The second word contains the rest of the data we want to process, so we need 2 processors for that. And what the processor takes is the pattern to match and the offset in the data, and yeah, basically that's what the processor is working with, and it's looking at the data. Does it match or does it not match? But then we have a problem with this not operator, because this not operator is going over the whole data. And I really worked on how should I operate this not operator, or an operator like that, where you have to process, you have to get a result and then process an operator on it. So first thought, okay, let's make a programmable network behind the processors. But then you actually lose this parallel processing. You make a block behind all the processors that should work on line rate. And the more complicated you make this block, the more time it will take to propagate through this block of data. So that will limit the speed, and it also will limit any scalability. And this was really a problem in designing this whole thing. And then the idea was, so let's try to see if we can transform it in software by making it actually a sum of products. You can always do that with Boolean expressions. And it really took me a while to get the term for this, to get it into this disjunctive normal form. But once I found this term, how you describe this form of expression you have, then it was really easy to find an algorithm that does that for you. And this is a QM algorithm. And you have actually libraries you can find on the internet. And then everything was solved. So I can give you a bit more detail on how these registers are working. I had 16 bits. I decided to make 16 bits for the register. That, of course, needs to contain a pattern. And, well, 16 bits seem to be a nice thing. So the register looks like this. It has a pattern for 16 bits. It has an offset 11 bits. That means that I have, in theory, the option to look all the way through all the bits of a 1522 byte frame. Of course, I need to tell the machine what it needs to do, and that's our 3 bits. And then there are some last bits to handle actually products that are larger than 16 bits. And that's been done by actually chaining the different blocks together with an AND operator. And Here there is a speed limit in the design, because you have to propagate, see if this block is true and this block is true, you have to have an operator here, and if you have, and this block is true, you ripple through all these different blocks. But that's the largest thing I could think of was matching it on an IPv6 address, and we have time enough to do that. But it's basically to end operations. And there's also a possibility to go smaller than 16 bits, and that's been done by using a bit mask. I'm not going into all these details. But that's too much on 1 bit or 2 bits or 3 bits. So basically, the software does this. It takes the input and changes it into 3, in this case, 3 registers to match the data. And I can demo this, I hope. So the demonstration is to send about 50 million frames. That's what I don't want to see, and then 1 frame I want to see. And then we go back to the other screen. Please? This is a hardware traffic generator. The question was, what is this software? And this is the interface of a hardware traffic generator that generates the traffic. So I'm going to switch off these streams and switch on these streams. So what you see here now is this interface here generates 14.8 million frames a second. And that's being received here. And I only look at one stream. So the other side is sending 1,000 frames a second, and this other guy is receiving 1,000 frames a second. So let's look at the output of this monitor machine. This is the output of the counters of the monitor box I was just describing. And you see here on channel 0 about a packet weight of 40 million frames a second. It's being wound down to 40 million. And the match packets are actually 0. And that's because I still have this filter on of the other demo in. So let's set a filter for seeing the frames from that are not from the MAC address where I sent this 50 million frames from. And by the way, you see here the internal representations of these different steps I tried to explain in my slides. So let's see what we get in here. That's only one. So we see here now coming in. So after the filter on this Ethernet interface, the monitor box is representing. We see frames coming in by about 1 a second. Look at the timing here. So what we're doing is we're sending 50 million frames, about 50 million frames. 1 frame we want to see, and then again another 50 million frames, with almost 50 million frames a second. And this PC can easily process this 1 frame per second, of course. Now to demonstrate that I'm not faking, let's remove this thing here. So now you should see here all the frames coming down. Of course, this PC cannot process this 50 million frames a second, but you can count them by the hardware. So the match frames here are 40 million frames a second. The PC cannot process that. Even the PCIX interface to the PCIX bus cannot process that. It processes about 689,000 frames a second that are being copied to the PC. Any questions about this? I see there a hand. In the back there was a hand. Okay.
Thanks. This is impressive work, thank you. My question is more general. It's how do you use this in a live setup? Because I imagine if something goes wrong here, the box crashes and you won't have the light replication from the source to the input to the output. Are there any ideas of making this using a really passive monitor? Because this is passive as you only get some of the traffic, but it still goes through the box, right?
Yes. Of course, you can use an optical tap to use only the input, then it copies things to the output, but well, hey, then it goes nowhere. So if you think that the electronics in between the part are a problem, then you can use, of course, you can use a passive tap there, if needed. The reason for not doing this entirely passive is the following. When we started with this, we had lines that were on the edge of what they could do optically. And if you put an optical tap in, you take some of the energy out of the fiber. And back then, there were situations where that could be harmful. So that's the reason to look for a repeater. You have then the possibility to do that, and you still have the possibility to do everything passive. On top of that, of course, you need to put this box into some line. And you need to take the line apart and connect it to the box. That is also harmful, but because we have these optical switches that really switch fast light in to another light out port, we can do that within about 20 milliseconds. So there's about 20 milliseconds of frame loss while putting the box in. Actually, it is a bit longer because some interfaces need to fire up or something, or MAC addresses might be learned, but generally that's below a second of getting the box in a line, and that's more or less acceptable. If you count it with this numbers of frames per second, it's still bloodbath, but yeah, nothing to be done about that. Can't imagine that I was that clear. I see a hand here.
Test. How do you interface the PHY with the FPGA? Is it SerDes or?
That's a technical question. On the front-end FPGA, it's a Xilinx front-end FPGA, and the firm Xilinx makes blocks for that. They call Rocket IO, and these are ZAWI interfaces. So you can buy, or actually they don't charge any money for them. So there's a block of Verilog code, of description, hardware description, you put into your FPGA. And actually, lots of what you see here was figured out by Force10 or Meta Networks before. And they actually bought this from Xilinx, this ZAWI interface. There are 2 ZAWI blocks in that, and that interface directly with this VICE, with this Xenfix XPEX. And there's another thing on that, is that between the 2 blocks there are 4 2.5 gig paths, and there is some hardware needed, some hardware resources in FPGA to deskew these paths, because some path takes longer than the other. But that's about the entire latency you get into the repeater.
Hello. You told us about frame rate of 1 million here.
Sorry.
You told us that you were able to dump 1 million packets per second using standard libpcap, but do you had to do any tuning, like interface polling or special libpcap?
Can you repeat your question or rephrase it? I don't think I understand.
Did you had to do some tuning on your Linux box to be able to capture
No.
1 million packets per second?
No, it was one of the design goals to do not really special things on the software here. So normally this 699 now here, about 700,000 frames a second. If you have to analyze 700,000 frames a second, you're already dead, because that is such an amount of data to see. So you really want to set your hardware filter to something like 1 frame a second, or even 1 frame a day or so, if you're really behind some weird thing in your network. That's where the box was designed for. And for that low data rates, you don't have to tune anything on the Linux part. So. Any other question? Then I guess, oh, yeah.
Have you thought about equipping your card with some memory so that you can define an, say, external trigger and capture an amount of data in, around this trigger?
It's one of the wishes. The card is equipped with SRAM, which we can use to online wait to store frames in. I just don't use it yet to do that. That's all. But it's one of the wishes that are on this for this product. But I'm working for a internet exchange which should ship bits. Yeah, we shift bits between different parties. That's my main job, and we needed this, and we with this whole thing with the pause frames, it was really, really useful to have it. But once the problem is solved, I have to do other things as well. So I'm not 100% of the time developing this product. We can use a student for that, actually. Okay, and I guess we're done. So.